And we found that it's best to actually turn the lights off for the talk so that. Okay, welcome everybody to the second session of the day in here. Got a couple talks for Mizumi Games. It's gonna be fun, and also a teaching demo, which will be cool. So the first group here is a design of a Plinko machine for trade shows for Mizumi. So go ahead and take it away, 20 minutes for the talk and then Q&A.
Hi everyone, thank you for coming. Today we're going to be taking you through our design process for a Plinko machine made for trade shows, and this entire project is sponsored by Mizumi.
Hi there, I'm Jack Mackey and I'm a computer engineer working on this project.
I'm Cade Ryder and I'm a mechanical engineer.
I'm Claudia Gabriel and I am a computer engineer.
I'm Mel Suleiman and I'm a mechanical engineer. For other members of this team project, we got Dr. Kevin Hart as mechanical engineering advisor, Dr. Robert Kearney as the computer engineering advisor, and we got two of Mizumi representatives, John Williams and Alfredo Barantes. Okay, starting with some background information. First with Mizumi as a company. The client for this project is Mizumi USA, a subsidiary of Mizumi Corporation. They are known for providing fixed and configurable components for the manufacturing industry, and it's headquartered nearby in Schaumburg, Illinois.
So the problem statement for our project, Mizumi is requesting a portable Plinko machine that showcases a variety of their own products while also drawing attention from the crowds at trade shows and conventions. Size is a very important factor in this project because the Plinko machine the company already has is too large and inconvenient for travel.
So on to some research on Plinko as a game. It's a well-known game of chance where a ball bounces down a pegboard and lands in different slots to determine a player's winnings. There's many different types of Plinko machines already available on the market, including the more physical boards that you may have seen on The Price is Right, or like home-based boards, and even virtual boards, which are more pachinko-y, more used for gambling.
To establishing our subsystems, we have user interface led by Jack Mackey, audiovisual also led by Jack Mackey. Packaging and assembly, board design and peg design are also led by Cade Ryder. I lead the electrical hardware and the power subsystems. The electrical housing, collection and return is led by Malik Suleiman. And following object design is led by Malik Suleiman and myself.
So first, when we started this project, we created the problem statement, did some background research, and then we kind of chunked it up into subsystems for each of us to work on, like Claudia just described. For the user interface, we decided that we would have a user interface to provide user inputs to the machine and machine outputs to the user, and then an audio-visual subsystem that would basically be focused on making the machine light up, make sounds, be more attractive to trade show attendees, get people's attention.
The electrical hardware for this project is mainly a microcontroller to power the machine autonomously, and then IR motion sensors to detect when and where a falling object passes through. And then power, of course, if you're working with electrical components, you have to have power.
Now moving on to the mechanical engineering subsystems. First off, we've got packaging and assembly. This includes the storage method used for travel for the entire system, as well as the assembly process on site. We've also got the board and peg design. The board design includes all the materials that make up the main play area of the game, and the peg design will consist of a variety of Mizumi components and features that they offer.
For the falling object design, essentially is the choice of the falling object is dropped along the Plinko board and bounces along the pegs. Collection and return is how the falling object will be collected after reaching the bottom of the board and how it will return back into the board for automatic play. And the electrical housing is just the housing for the electrical components that will be used.
Now, under the overall project objectives and constraints, there were several constraints that Mizumi required of us, mainly being the project shall mainly comprise of Mizumi components. Project shall not exceed spending limit of $2,000 for Mizumi related components, and project shall not exceed spending limit of $1,000 for non-Mizumi components. The project shall also include an automatic and manual game version. Project shall include a falling element dropped through a series of Mizumi components.
Next, we formulated objectives and constraints pertaining to each specific subsystem. For UI, the design should have a switch to toggle the Plinko machine on and off. The design should have a button to switch from automatic to manual mode. The design should incorporate a screen to display helpful information to the user. The design shall not require more than 18 I/O pins. The design shall not draw more than 0.5 amps while in operation, and the design shall be readable from a distance of 10 feet. Moving on to the audio-visual subsystem, the design should react to stimulus from the user and the falling object. The design should incorporate multiple different colors, and the design should clearly indicate which basket the object lands in while in manual mode. The design shall not draw more than 2 amps at full brightness. The LED should be capable of displaying full RGB color, and the design shall not produce more than 1,000 lumens or 80 decibels, because that would be a little annoying.
As onto the electrical hardware and power objectives and constraints, the sensor shall be able to detect a falling object in motion. Sensors and motors shall be compatible with either 3.3 volts or 5-volt power. The microprocessor shall have an accessible development environment for ease of coding. Microprocessor shall have more than one core for automation purposes. Microprocessor shall have at least 28 general purpose in out pins, so we can configure our peripherals. As for the power, the Plinko board shall be able to run with either 120 volt AC power or an 8-hour battery. Power shall be able to level shift 3.3 volts and 5-volt power to the peripherals and microprocessor. The amperage shall not exceed 2 amps for the microcontroller.
Now moving on to the objectives and constraints for my subsystems. First off, we've got packaging and assembly. The Mizumi chose the Nanic 975 travel case with the dimensions listed on the screen. You can also see the picture down below. The assembly process should be easy to follow and should take no more than 10 minutes. The design shall be durable enough to withstand typical travel conditions while in the travel case, and the system should not weigh more than 50 pounds for ease of travel. Now moving on to the board and peg design. The system should be able to withstand use for 8 or more hours straight, simulating what a trade show or convention would be like. The peg shall be comprised of 20 or more Mizumi components, and the design should allow the game ball to be dropped from anywhere along the top of the board, providing a more immersive user experience.
For objectives and constraints for my subsystems, for the following object, it should weigh less than 0.5 pounds, should have a volume of less than 5 inches cubed, withstand an impact of 0.2 foot-pounds, and it shall include the Mizumi logo, shall fit into a collection and return system. For the collection and return, it should be able to carry the weight of 10 falling objects, should be unloading an object every 15 seconds or so, and shall not be in the Plinko pay area, and as well as shall be able to be turned off for a manual setting, and shall return the object back into the Plinko board. For the electrical housing, it should have a volume less than 1,000 centimeters cubed, weigh less than 1 pound, be hidden from the player's viewpoint, and be contained on the board and should be easily detachable.
So now we have some objectives and constraints set up. We can find some initial design concepts. Initial design concepts for the display focused on readability, character size, power consumption, and cost. 3 main solutions were considered here: the Hub 75 LED matrix, a Focus LCD panel, or a 14-segment display from Cirqua in an array. As for buttons and switches, the focus was appearance, reliability, and cost. Visual design concepts valued customizability, brightness, and power consumption, which led us to the Fit 0810 LED strip, single color, the NeoPixel LED strip, which is RGB and full programmable, and the NEIL IO signal beacon. And this beacon is really nice because it actually offers different colors and sounds, which is kind of a consolidation of both audio and visual. Moving on to down selection, we decided to go with the Hub 75 RGB LED matrix because it was the most customizable by far, and it was able to get sourced cheaply from MSOE Tech Support at a discount. For the LCD panel was eliminated because it just wasn't a good display. You couldn't see it from good angles and it wasn't very bright. And the 14 segment display was prohibitively expensive and also restricts the total number of characters and types of characters you can display. The DP/DT toggle switch and rugged metal push button were selected together because they go together well and their metal fabrication makes them reliable and durable. Onto the audio visual down selection, we decided on going with the NEIL IO signal beacon as the aforementioned combination of the audio portion, the buzzer, and the visual portion of the actual light up beacon. It was just really nice. And those would be kind of outside of the board. So I also went with the NeoPixel LED strip to kind of give light around and inside the board as well.
Moving on to electrical hardware, Misumi sold sensors took priority over other brands. Preferably, the sensors should sense when and where an object moves past them or be small enough to be placed in each well. The microcontroller considered were based on cost, familiarity of coding environment, memory storage, and the amount of GPIO pins. As for power, the input will be 120 volt AC as a baseline, step down to at least 3.3 volts and 5 volts for peripheral microcontrollers, and it must be reliable, no voltage drop or current drop. As for the sensor down selection, 13 sensors were considered, 6 of which were non-Misumi and 7 of which were. Misumi took priority as they are our sponsor, and for this was specifically for the collection system. And at the end, the through beam IR sensor was chosen for this project. As for the microcontroller down selection, 3 major microcontrollers are considered. We have Raspberry Pi 4 Model B as our winner, given its customizability, the room for growth, and it has multi-cores. It also has access to RGB matrix hat and RTC, so it provides power and configuration for the RGB LED matrix display that we have already chosen.
For initial design concepts of the following object, it needs to be easily grabbable, and it should fall down the Plinko board without potentially getting stuck. Some choices were a golf ball, ping pong ball, a flat chip, a foam ball, and the dice. For electrical housing, it should have good electrical and thermal properties, have enough space for the electrical components to fit in. Some of the choices were an off-the-shelf polycarbonate box from Misumi, a GPO3 housing, and building the electrical housing into the board itself. So for the following object design down selection, the weight, durability, size, customization, cost, and coefficient of restitution, the ease of return were considered. The golf ball ended up winning because it's durable, so it won't be damaged by the peg when it's falling down the pegs. Ease of return because the spherical shape makes it easy for collection and return. And coefficient of restitution makes the golf ball a good bouncing candidate for a good enjoyable Plinko game. For electrical housing, consideration was cost, machining, use of Misumi components, thermal and electrical properties. The polycarbonate plastic box from Misumi ended up winning because it is from Misumi, our sponsor, and it has good electrical thermal properties. And it's already off the shelf, so that makes it a good choice. For the initial design concepts of collection and return, it needs to be considered something that can put a falling object back into the Plinko board with good upward motion. So some of the initial conceptions were flat belt elevator, a chain elevator, and the Archimedes screw. So some of the consideration was cost, space, ease of build, connection to a lifting element, and the speed that's available. So the chain elevator ended up winning because it has good speed available from the motor, and the connection to a lifting element is fairly easy because of the connecting link with brackets that can attach a lifting element to it, and it's fairly easy to build. That's the chain elevator is the one we went for.
Now moving on to the board material down selection. So on the left side, you can see a bunch of the materials that were considered for the gameplay area. Also on the top, you can see some of the major categories that we graded all of these materials in, as well as the importance or weight of each of the categories. Some of the categories that we thought were a little more important were the durability, smoothness, appearance, weight, machinability, and customization. There were some other categories we graded on, but we figured those were the most important in its application. And then down on the bottom there, you can see the individual scores for each of the materials that were considered. The top three ended up being fiberboard, acrylic, and plexiglass. And then for the back of the board, we ended up going with the medium or high density fiberboard. This is a good material because it's durable. It's also good for other components to be able to root into, just providing a solid base. And then for the front of the board, we ended up going with acrylic or a polycarbonate because they're essentially the same thing, which is a good material for the front pane since it's transparent and scratch resistant. Now moving on to the peg component down selection. As I mentioned earlier, we needed at least 20 Mizumi components to fit onto this board. So far I have a list of 18. This is comprised of linear shafts as well as some rotary shafts, which you can see some pictures of on the bottom. They are stepped and threaded. And the specs that I went for each of these components was a diameter of 15 millimeters with a length of 50 millimeters. Then I'm going to be, as I mentioned, I'm going to be looking for some more components because the board I designed includes 27 Mizumi components. So I will also be looking for some dowel pins and any other components that fit the spec requirements for the board. Now moving on to the CAD model. This is a work in progress. There's a few more things that do need to be completed, which we'll get into later. But for now, on the left side, you can see the front view of the Plinko board where I've called out some of the major components, such as the Mizumi components acting as the pegs, the acrylic or polycarbonate front pane, the falling object golf ball for reference on size, as well as the medium or high density fiberboard as the base. Now moving over to the right side, you can see the back of the Plinko board. On the top there, you can see we've got a mounting platform for the LED display. You've also got some holes in it, which will be able to mount those beacon lights. And you might also be able to see that the threaded end of the Mizumi components stick through the back of the board. This will be used as the main fixation device since we will use that with a washer and a nut to secure the components onto the board.
For the CAD model for the lifting assembly and housing, it's mainly contained on the back of the board. And for the collection system, there will be a ramp at the bottom of the Plinko board that'll be rolling golf balls into a collection area for holding. For the return system, it includes a stepping motor that'll attach to a roller chain sprocket. Roller chain sprocket will be wrapped around and also wrapped around an idler sprocket above. And as the motor rotates, throughout the chain, there's connecting links and a lifting element all throughout the chain. Then as the chain rotates, the lifting element will pass through the collection area to lift the golf ball up and eventually drop the golf ball into a ramp that'll lead into the Plinko board.
So now for some of the future CAD progress that I was mentioning earlier, we need to combine that main Plinko board model with the collection and return model, which will give us a good overview of the entire system. We also need to configure the arrangement for the IR sensors since they're just kind of thrown in there at the moment, which will likely require to block off either a collection bin or two to be able to fit these sensors into the board. We also need to add the audio and visual components, such as the light beacons and the speakers as well. We need to find none more Mizumi components as pegs, which I mentioned will be hopefully some dowel pins and anything else you could find on their website. Also need to configure the packaging arrangement and assembly method. I think we sort of have an idea. We just need to finalize this idea. We also need to decide on material selection for ramps. This will most likely be the medium or high density fiberboard, which is the same as the base of the board. But it could be, we could resort to polycarbonate so it's see-through as well.
Aside from the mechanical components for this project, we will also be working in a simulation environment so we can code the IR sensors, the audio-visual components, and the user interface. We will be working on the Raspberry Pi 4B, which is a fully fledged computer, and 2 IDEs are already installed. We have a Python Thonny and a C++ Greenie. This is going to be our language of choice, as embedded C is what we are taught here at SOE. Aside from that, the fully fledged computer allows for SSH, so a secure shell, a more, headless programming essentially. So we do not need to be plugged into the board to program on it.
So with all that being said, these are our current specs. Some highlights are the power is getting supplied through a 120 volt AC wall outlet. The Hub 75 matrix is a 64 by 32 resolution. We'll have 27 Masumi components featured as pegs on the board. And the motor being used is a stepper motor. These are our bill of materials as it stands currently.
So what's next for this project? As I mentioned before, we need to finalize the CAD model and start ordering the required parts. Once the parts have arrived, we will begin testing and be able to integrate this testing into an initial prototype. Once we have the initial prototype, we can then test that, make sure everything runs smooth, which will lead into our final design, hopefully by spring of next semester.
Just our references for our background research and relevant patents that we may have used.
All right, thank you all for attending, and we would be glad to answer any questions.
All right, thanks, guys. You just flip the white light switch there on. Yeah, that's good. Okay, so we'll take questions, committee first, and I guess John, if you have questions also, fire away.
Why'd you choose MDF?
Sorry, what was it?
Why'd you choose MDF over plywood?
I just figured it looked slightly better, had a little better appearance. Also that it was more customizable. We can do more like engraving options. We were thinking of engraving the Mizumi logo into the back of the board, which would look really nice. I also figured
Is it being used as a structural component?
it's somewhat structural because any component mounted on the back of the board will route into that fiber board. But we're also going to have a sheet of polycarbonate like pancaked with that fiberboard, which will, I think, add to the appearance as well.
Yeah, I would really caution you on using MDF as a structural one, especially if you're traveling. If it is traveling, the difference in humidity from one location to another it is shocking how much it expands with humidity.
Okay.
And so bolts that you had tightened down well will no longer be tight if you move it to a different location. It seemed like some of your constraints for both power and logic and the requirement of multiple cores seemed like you had picked those to tee yourself up for making a choice on a specific system. Is there, like, it seems like you're using IR sensors and flashing LEDs. I don't necessarily understand the multiple cores or why you knew that you needed to go from 3.3 to 5 volts.
So microcontrollers, their logics are based off of 3.3 and 5 volt logic. Most of the microcontrollers work on 5.3. It's more so that we don't short out the microcontroller itself. And having multiple cores allows for automation and how do we describe it? It's optimization of the core usage. So if we're able to have more cores, it will be less on the main processor and more on cores to handle various tasks. So we can run it simultaneously instead of having to wait until this task can be completed. Sorry, that was very heavy.
I've done this a fair amount. So yeah, I just, but we can go on to something.
Okay, other questions?
So thank you for a nice presentation. Just I have one, basically suggestion. When you present the CAD model, it is good if you put like some like dimensions, like to give the audience like looking over the size. Second, I have a question for like mechanical engineers. So what like concepts from mechanical engineering? Because like it is a very broad question. Like did you use in this project? For example, how do you are using a gear motor, right? How did you like? Do you have any calculations that like what power you need? Like all of those calculations, the small calculations that you learn from like mechanical engineering courses.
And to build on that, how did you choose a stepper over a DC or brushes?
So I chose a stepper motor because it was easier to program for the computer engineering and it's more familiar. And for the calculations, I just did the weight of the roller chain and the weight of the falling objects that would be lifted by the roller chain and did torque calculations. And then for that torque, I went into the Masumi catalog, found a stepper motor that would have that torque and the required speed I would be needing. And that's how I chose the motor.
In the automatic mode, is there any randomization of where it drops? It's dropped in the same spot all the time?
I think it will drop in the same spot every time just because it's quite hard to introduce something that would move that. Because we also have the display or the mounting display for the LED board on the top back of the board. So that kind of limits where the ball can be dropped. But the automatic mode will mostly be used for purposes of drawing in attention from the crowd. So hopefully once people actually get up there, then automatic mode will go off and they can choose to drop the ball from wherever. So their experience will be more variation.
The pegs, how specifically are they mounted and what are they mounted to?
So I can take it back to the model. So they have a threaded, stepped and threaded end, which sticks through the back of the board. So I'll be using a washer and a nut on the back of the board to secure them, sandwich them to the.
So the little shoulder, the peg, and a nut and a washer on the back, and what's in between?
Just the medium density fiberboard.
So those things are gonna be dedicated over and over and over for 8 hours a day. And you have a tiny little shoulder.
Yeah, we were thinking of using 3/4 inch or maybe inch thick medium density fiberboard. That way there's a steady.
Yeah, I would think you need to do a little more engineering on how those are actually secured into that board and don't just rely on a small shoulder on the peg against the fiberboard. Because for one, it's gonna break down over time. And number two, the bounce that you get off of those is really going to be entirely determined by the properties of how that peg is fixed at its base. If it's a flexible mounting, it doesn't matter what the peg is or how stiff it is, bounce is going to be because its footing is giving way. Even like the sound of it is going to be determined by that connection, not necessarily by the peg itself.
Okay. We'll definitely test it too once I'll look into it more as well, but
Yeah,
we'll do
before you-
testing and.
Before you plan out all and start drilling holes and everything, like get a couple and stick it through some fiberboard and drive a golf ball on it and see what happens.
Thank you.
I think it's good here.
Yeah.
Okay. Other questions? We've got about 1 minute. John, you have a question?
One question for me, I mean, you guys have given us updates as we've gone along, so that's been good. We've had some discussions on that, but for the pins, especially going into fiberboard, have we thought about replacement over time? So if we're using this at a dozen trade shows a year and we're hitting, 8 hours a day for a week every time, we might have some damage to the pins over time and corrosion with, general environment. We're in San Diego, Boston, you're gonna be seaside for a lot of these. You might get some salt in there. For replacement of pins, is that something you guys have thought about for future state?
Yeah, so the front sheet of polycarbonate or acrylic will just be screwed into the top. So you'll just be able to undo these screws, take off that front sheet, and then obviously you'll have to undo the washer nut on the backside to remove the pegs, and you can just throw a new one in.
Okay, we gotta move on to the next talk. Let's thank this group. Good job, guys. We have another Mizumi talk. Yay! Yeah. We're gonna play some pinball.
This must be a fun place to work. I'll move some over here.
The next pinball machine. Pinball machine.
Yes.
But you can hit the white place. Yeah, it's just a little easier to see the slides. Got it. Okay, so we got one more talk, Mizumi Fun Games. This one is a pinball machine. So go ahead, take it away, guys. 20 minutes of the talk and 5 minutes Q&A.
So this is gonna be our design of a Mizumi pinball machine.
I'm Riley. I'm Luke.
I'm Sam Last.
I'm Samuel Bone.
And then I'm Scott. So for the project proposal and constraints, so we were tasked with designing and building a tabletop trade show demonstration unit that utilizes both motion and a large number of Mizumi components to catch the eye of trade show attendees. So a couple different constraints that we had. Originally, the size envelope was going to be 600 by 350 by 300 millimeters. But that was changed to fit into a Nanic 975 travel case, which is 762 by 533 by 457 millimeters. For power, it was going to be 120 volt standard AC outlet or battery power, which lasts up to 8 hours. For portability, they wanted it to be able to take less than 30 minutes to set up by a single person. And then some extra constraints that they would like to have was to have a time limit option to get more people to use it, and also to have an automatic scoring feature on the pinball machine.
So for our first steps in our cabinet design, we actually got our general pinball dimensions, our usual pinball machine from our industry contact that Jersey Jack Pinball. And then we scaled those dimensions down to fit within the constraints that we had. And we also maximize those dimensions. We want to maximize the playfield dimensions that we could get to have the most fun that we can get out of the machine. And we accounted for, when we were maximizing those dimensions, we accounted for the wooden panels on the side and then left about an inch gap or 25.5 millimeters on all sides and a little bit more on the top so that we can have room for any external features and for any foam packing inside of the travel case. So for our first cabinet design for the framing, we used the Mizumi frame software. We used their HFS 5 2020 extrusion framing. It's 20 millimeters by 20 millimeters. Our original design, the height here was a little bit too tall. It didn't leave enough room for the playfield. The playfield would stretch from there to there about, and the height we would get for the playfield was too short, so we needed to lower that. And then the width of the back box is actually on a slant as it goes down. It's kind of a trapezoid shape. And this original dimension was scaled from a real back box, but that was off of the top dimension. So this was too long and it was actually ended up being short. So for our second iteration, we shortened both of those dimensions so that would work out. And then for our third and final iteration of the framing, we removed 2 posts so that we could extend the playfield longer, we get a couple more inches of the playfield, so it go beneath the back box. And then we added a bar in the back for ease of mounting the playfield onto the frame. We then exported the framing into SolidWorks and we added the wood panels, we added the hinges. The back box rotates off of this. That's in the open position. There's a cam lock in the back that holds it in the open position. And we added the metal side trim here, which will screw on. And we have the playfield glass, and there's actually plastic trim in there, which is what the playfield glass is actually touching, so it does not get scratched. And then the apron will be added and a lock bar, at the bottom to hold the playfield glass in, and those will be fairly easily removable if you ever need to take out the playfield glass. And then for our custom parts, we use Mevi through Misumi, and those parts can be made. You can just upload a CAD model, and those parts can be made through processes such as CNC milling or modifying the sheet metal. Those parts that we're making through Mevi is going to be the hinges, the side trim, and the lock bar once it's designed, and then the ramp structure for the playfield, and then the apron. The apron, once we design it, will have an opening so that we can view the pneumatic components for the plunger mechanism to launch the ball. And then that is a open sourced apron just for as a reference picture.
So during the cabinet design, we're also thinking about playfield design and what kind of theme we want for the game. So we decided to go with a MSOE theme focused on Roscoe Raider. So because of the connection with MSOE, we got in contact with marketing to make sure that the game meets what MSOE wants, and also get creative help with the artwork for the cabinet and the playfield. And one of the requirements that the creative director gave us was to connect each major component that we had previously selected and connect it back into the theme. So the theme starts with the player who finds themselves out at sea when they come across Roscoe Raider and a ship full of treasure. So the player decides to launch a cannonball at the ship, which you can see down here at 1. We're going to have our pneumatic system for the cannon, and then it rides up the shooter lane and it falls through the hole in the top of that ship and comes down the ramp. And then after the ship is sunk, the goal for the players to collect as much of Roscoe's treasure and his materials as they can. And in order to do that, they have a 3-minute time limit, because that's the amount of oxygen that they have. And at the end of the 3 minutes, they need to either return to the surface or they'll drown. So once underwater, the first goal should be to collect Roscoe's materials, which are M, S, O, and E. M is the arrow on the left. 2, that's the target. S is connected to the spinner that goes through the loop. O is a stand-up target to the left of the ramp, and then E is the ramp. And once MS, O, and E are collected, it qualifies a multi-ball. In order to start the multi-ball, the player has to hit the stand-up target to the right of the spinner. And then from there, the main goal is to collect as much gold, which are those stand-up targets in the top within the orbit. So if they shoot it past Roscoe, it'll bounce off the targets and then bounce off the pop bumper in the middle. It'll be randomized, but it's not going to be very easy to get back there because there's going to be a small Roscoe Raider figurine that's going to be on a mechanism that will move him back and forth, and that's the little green box will show his path of motion over by the fort. And if the player happens to shoot the ball into the scoop over at 5, it'll hold on to the ball for a few seconds, which is not very good because you have a time limit and you can't score any points if you're in the single ball mode. But Roscoe also does not move while that happens, and after he lets go, he's tired, so he moves slower than before. So if you're in a multi-ball, it might be beneficial to shoot it in there to stop him when he's far away from the entrance to the gold, so you can shoot your other ball in there and collect gold. Then in the last 10 seconds of the time limit, the game will signify that you're reaching the end, and the player's goal is to shoot it back in that scoop that previously held it, and that resembles returning back to the surface, and the player gets to collect a bonus based off of how much gold they collected during the game. But if they fail to shoot it in there, within the last 10 seconds, the lights will slowly fade out, resembling a death by drowning. So some of the mechanisms that we're buying from Pinball Life are the flipper mechanism, the slingshot, the pop bumper, the spinner, and the scoop. And for the flipper mechanism, we picked the highest power solenoid to ensure that any shot that we put on the playfield can be made because it has enough power. And then for the ramp mechanism we bought it from Dizzy Jack Pinball. You can see it here featured in The Godfather. On the left, in the circle, you can see the ramp when it's in the down position. And then on the right, you can see when it's up. So when it's up, it allows for the ball to travel underneath the ramp. And it also allows for another path to a wire or return ramp.
All right, for the plunger mechanism, we're planning to use a pneumatic piston to shoot the ball out. So we're starting off with a solenoid just to actuate the pneumatic piston. And then we're also going to use another solenoid to regulate the pressure. So it'll have two different shots with this solenoid. One, so when the ramp's down at the beginning of the game, then the ball will just fall down. And then when the ramp is up for a multi-ball, then we'll use the higher pressure to make sure that the pinball can make it all the way around the ring. And then there's the rest of the diagram, the piston that we plan to use. Here's the calculations that we use to get the volume of the piston. This is what to get the volume of the tank that we need and how long the compressor is going to have to run for. Then here's a linear actuator or lead screw that we're using to move the Roscoe Raider back and forth. We're working with marketing to get that figurine that we're going to use. And I'll just move back and forth there.
So then for the hardware circuitry design, we have just a couple of main requirements that we want. So first, we need some sort of controller board to interface with all the peripherals, which we are going to be choosing. We'll go forward with that. And we're also going to need some driver boards that control high voltage components. And then to fit with one of the constraints that Misumi gave us, we need a power supply that runs off a 120 volt AC standard wall outlet, which for our case, we're going to be choosing a 48 volt power supply from Misumi to utilize all the high voltage components because the flippers, the slingshots all have a maximum voltage rating of 50 volts. So that's as close as we're getting to that. And then additionally, we wanted to have some sort of main programming language that we teach at MSB, so either embedded C or C++ or Python. So there was two different choices that we were going with. So first, an Arduino microcontroller with additional circuitry, or the fast pinball architecture. So some of the pros between those two: for the fast architecture, it has good documentation across all of its website with wiring together components and coding together. And it's a thing that's widely used across homebrew pinball machines for people. So there's tons of tutorials available online on YouTube or websites. And it essentially has a plug and code kind of mentality where all the driver boards and circuitry is already designed for you, and you just have to plug it in, and basically you just code all of the different aspects of it, which makes it easier for driving those higher voltage MOSFET switches. For the Arduino and circuitry, its main pro is it's cheaper and it's very widely available and easy to obtain or replace in case something is broken down the line. It's also very easy to wire up the targeting and LED wiring. And again, it's a common processor used in industry for prototyping and different projects. So there's help for support and code. Some of the cons: the fast architecture, it's expensive. We'll go into that in the next slide. And it's also, which makes it more difficult to replace for Misumi or us if the board were to break during prototyping or anything else like that. For the Arduino circuitry, one of the cons is you have to design and build the circuits for the high voltage driving of the flippers and slingshots, pop bumpers, all the higher voltage components. There's not as much documentation for wiring some of these components because they don't really possess data sheets. And it's more difficult time with creating the working flipper functionality for prototyping. So here we can see a little bit of the cost. So as you can see, like the fast, it's almost $600 for everything that we would need. Whereas an Arduino, and if we build our own PCB, it's going to be, you can get an Arduino for around $50 off Amazon. And circuit components could be anywhere between like $5 to $20 depending. So we decided to go with the Arduino and circuitry. So the main point of additional work will be with the high voltage driver boards. So we can kind of see a schematic from that here for the 48-volt parts. So essentially the inputs will be connected to the Arduino GPIO pins, which are pull down resistors. When they're driven logic high from those IO pins, it'll activate the gate voltage, which will allow the voltage to go across the MOSFET switches. And that will allow the circuit to connect on all these different high voltage devices and will allow them to essentially activate and have that power directed through. So for the MOSFET component selection in that future PCB board, we will need to have a voltage rating of greater than 48 volts to accommodate the power supply. And we also wanted a current rating of around 12 amps, just because we measured the resistance between some of those fluid mechanics as around 4 ohms, which I don't really think is going to be accurate, because in some outside research, most pinball machines only draw between 2.5 to 3 amps. So I definitely need to test that going forward when we actually receive the power supply to see how much current really will draw. But just to make sure that there is going to be no issues with that, I selected a MOSFET that has a maximum current of 30 amps running through it. So it should be totally fine in that regard. And it also has a drain to source voltage maximum of 75 volts, which is almost double what we really need. And then the gate driving voltage is at 4.5 volts, which the Arduino that we're going to be using, the Arduino at Mega, has driving voltage of either 3.3 or 5 volts. So if anything, we could just have a resistor to slightly decrease that gate voltage. So there's 2 devices. The ramp diverter needs 20 volts and the scoop needs 24 volts. So instead of going out buying new, totally different power supplies and putting more budget, it would probably just be easiest to use some sort of voltage divider in order to get those voltages down from the 48-volt power supply that we're going to be using. So you can see some of the calculations on the resistances that we're going to need for both the 20-volt and the 24-volt sources.
Now going into the software section for our pinball machine. It'll be a C-based state machine that is interrupt driven, and it's going to be simplistic for speed, since our game is highly dependent on timing for our board components. It's going to be predictable for the player. So we start out with the initial setup to initialize all board components, and then transition to the idle state to wait for the player to start the game, where all sensors and components are locked. So nothing interrupt scoring or unwanted actions occur before starting. And then once the player starts the game, it'll start the main game loop and the start timer of 3 minutes. And in the game loop, it'll allow interrupts to be fired. And once an interrupt is fired, it'll perform a game function related to the sensors or other game components. And it'll update the score if need be, or reset the game object as need be. And after that, it'll clear up any interrupt flags and transition back into the game loop. And after the 3-minute timer is up, it'll go into the end game to display the final scoring. In our main program loop, the timer is displayed on a 7-segment display for the player, and the light show on the game board will be influenced by game operations to communicate to the player on how their game's going, along with sound effects to communicate game status to the player, or based on timing or game actions to further engage the player. Sound effects will also communicate by laying feedback to know main objectives in the game and which are good and bad. For scoring will be a volatile global variable in memory, since it'll be changing a lot, and we can add safety to that so scoring does not get corrupted. It'll be updated through interrupts. Interrupts are good for our C-based programming, because they're very fast and won't heavily impact timing on our game board. And it'll be displayed
for the player through a 7-segment display. And be very simplistic and interpretive for the player to know how to play, how their game is going if you've never played pinball before.
So going forward and kind of summarizing what we've done so far. So this first semester, we had initial brainstorming of the playfield and the cabinet designs. Then when the time we go about designing the cabinet and the playfield. And then a lot of that finished out with determining the main playfield components and getting different component selection and such. So going forward into this break in the second semester, it's going to begin the prototyping phase of the playfield and the cabinet, as well as coding the firmware for all of the different actions and scoring for the machine. And then after finishing the prototyping and doing all the tweaking, we'll begin assembling and manufacturing the pinball machine in its entirety, and then begin testing and integration of all the different systems.
So during prototyping and testing, a lot of the prototyping will be done with 3D printed structures or just scrap material from the machine shop here. Primary material will probably be cardboard, CC, the band for all the guides. And then during prototyping and testing, the power to the solenoids will need to be adjusted to ensure shots are made, but it's not too fast. And then during play testing, we'll have a variety of people with different skills play the game to determine how often the pneumatics are driven to see how big the tank needs to be, and to also check for wear and any other bugs that we didn't account for in the initial design.
So the main goal of this was to use as many Misumi components as possible, and here's our updated BOM. As of late, we still have extra more components that we have to put on there, such as like fasteners and some other plastics that we need to add.
So then, yeah, we just like to give a special thanks to John Williams and Patrick Nalen, our Misumi sponsors, as well as Eric Mounier, who is our contact at Jersey Jack Pinball, who's the game designer. We would also like to thank Dr. Farrow, Kristen Dunn, Dr. Patterson, and Dr. Hart.
Any questions?
Okay, thanks, guys. Hit the white light switch there, please. All right, time for questions. Committee members first, and then general audience first. Committee members and John.
You go back to your. What are you powering with that? So the 20, so that we need one with 20 volts and one with 24 volts. So firstly, Greg, what is it that you're powering? Two of the different systems. So one is the ramp diverter that we talked about before, and one is the scoop, which Sam mentioned before. Here I can show pictures.
Yeah, Scoop's 24 and the ramp's 20.
So this would be like the ramp diverter. You can kind of see it in these pictures where it goes up or down depending. And then the scoop is this mechanism here. And can you go back to the fire? No. So you're not gonna get enough current there. Okay. It's none of those things will move. We can talk about it, but you'll have to figure out another way. And then the selection for the flippers, I wasn't sure I understood. So you picked that specific one because it could move any size pinball. Is that what you're saying, Gary?
Yeah, so the solenoid on that has more power, so it rotates faster, right?
Did you compare that to a pneumatic version at all, or not?
So you have like some pneumatic components that are in this, yes?
Yeah.
So you're talking about some compressed air, right? Like using some of these. So how are you recharging that compressed air? Like where are you getting your air from?
We'll probably have an outboard compressor though. Missing probably provides.
Okay.
Yeah, they could have some.
We're still in the works on storing where the tank is gonna go and what the compressor's gonna
Okay.
be.
Is that common like for pinball machines to have like a?
No,
We're just gonna use as many missing parts as possible.
yeah, that's our way to do it.
Cause I was thinking about this, I'm like, I don't remember like playing pinball and then all of a sudden like hearing some compressor come on, like, I don't remember that around.
This was one of the easiest ways to add more, assuming.
As far as I know, there's not been a home brew pinball machine that uses pneumatics or anything. It's all electrical solenoids.
So the most up-to-date cab model, is that the one that you showed was kind of like the fold down situation? Um, Is there like a display on the top side and is there wiring going to that? Like how is that? Like how does the wiring
Yeah,
sort of work when you fold it down?
go back to,
There will be a display on the top part of the back box.
yeah, so in the back box will be the display we mounted, and then there will be a plastic piece that locks in that shows more artwork. And then when it's folded down, there will be like a small corrugated tube that all the electrical wires will go through. It's pretty common in games,
Yeah, okay,
other games now. But
that's fair.
yes, we do not have actual, any of the other components in this model. It is purely just the outer shell.
I like the ideas of the game though. It's clever. You know, so that's cool.
Yeah, we can.
We're drowning.
We can thank Kristen for a decent amount of this. She was the one who thought of making the time limit be the oxygen. And yeah, she came up with a couple other good stuff.
Yeah.
It was really fun working with her so far.
Cool. It's funny that Eric from Jersey Jag, he and I were in marching band together. It's kind of fun. And Wisconsin.
I was gonna put DQ.
15 years ago. That's funny.
If you want to explain that to everybody.
Maybe later. All right, other questions?
You guys thought. The story is good, I like it, but have you thought about how much you're trying to convey with it? Because with like this, I feel like this is the opposite problem the other team has, like they picked overpowered. Like it's a good solution, right? But they picked overpowered for what they need, but you guys are trying to show so much with your story that I'm not sure an Arduino is gonna get you there. Like, I feel like you need to think through like how you're gonna show a lot of that story with it. Because if you don't have the visuals that Dr. Hart was asking about, like it's gonna be hard to show that if you don't have a more elaborate display. So, yeah, I mean, we have thought about if we need to have more pins, we can add additional Arduino Unos to control different peripherals. So that's what a lot of people do with Arduinos. They'll have like a main, like an Arduino Admega that's like the main kind of scoring thing. And they'll have like an Arduino Uno that focuses on like all the LEDs, and then one that focuses on all the audio, and then just have them communicate with each other.
And a lot of the game design will be communicated through the lights and audio, which is very low cost for processing power.
John, how do you feel about it being so MSOE centric?
It's interesting seeing the different designs, because we've got a couple of different groups that are doing similar types of projects for us.
Okay, cool.
It works both ways for us. One, it shows off that we're working with universities, so having a very university-centered one allows us to highlight a different aspect of our business, which is unique compared to some of the other ones. So, I will be curious to see how you can sort of tie in Masubu a little bit on there, so that it's all integrated.
Yeah.
The story is definitely interesting. I am worried a little bit about the complexity of your storyline at a trade show when you've got 3 minutes for a line of people coming through. Like, those of us working the booth will understand your story because we'll be able to see it all day. But people that are coming in just to play the game for a minute, 2 minutes, 3 minutes, are they going to grasp everything? It's just gonna be a bunch of flashing lights in their face, which is not necessarily a bad thing either for,
Yeah.
How do we communicate that story across, without having, a full page storyboard to go with it?
Yeah, normally on a lot of games, on the apron down in the corner, they have just a little plaque with the main roller steps. And we wouldn't, on that, we probably wouldn't put as much detail I put into it on here. It would just be like white MSOE to qualify multiple, hit that.
That was something encourage you to sort of think about how do we streamline that for consumers that are not familiar with that, so we can all.
Yeah, I could have made the whole playfield layout a lot more complicated, but
It's already pretty complicated, so I think you're plenty of complicated. All right, we gotta move on. Thanks, guys. Thanks, last, not least. Yeah, Ivan's, I think one of the committee members here.
Yeah. Yeah.
I'm the light story.
No, you're fine.
No problem. No, thank you. Hey, you guys ready? I'm looking at. Oh, sorry, come on in. Okay, last talk in this session is kind of an educational talk working STEM to STEM. So 20 minutes of the talk, and then Q&A. Go ahead, guys, take away.
Today we're going to talk about the STEM to STEM teaching technology project brought to you by
Dan Gonzalez.
What's the more?
So the project statement for this project is creating 2 new lessons or demonstrations for STEM to STEM. One demonstration will be conducted in the MSOE lab. Another one will be a mobile or transportable demonstration. Each should be 75 minutes long and should be able to accommodate a group of 10 to 25 students. The cost of both experiments should not exceed $1,000 and it should be completed by April 1st of 2025. Our 2 most important criteria for this project is student design freedom, as well as incorporating a variety of learning styles.
All right, so now we're going to go into some background research. We're going to talk about what STEM to STEM is. I'm going to talk about the current state of the program, some learning styles and general learning concepts, and then some other psychological concepts that we want to try to integrate. So what is STEM to STEM? STEM to STEM is an educational program created by Rachel Hunter and Will Bott to provide a STEM education and rowing experience to underprivileged children. There's over 20 different locations that do this program that serve kids from middle school to late high school. Here at MSOE, it takes place in the STEM Center, and we teach middle school students. So they do sessions once per week for a period of 6 weeks, and they have 3 of those blocks per year. So before the lesson, it takes about 45 minutes. They just have like a snack, do an icebreaker, try to release some tension for the day because it's an after-school program. Then they go on to a lesson, and then they do an activity. So the lessons take 10 to 20 minutes. It can't be too long because the children get a little rambunctious, they have high energy. So the activity afterwards is more geared towards like design and supplements the activity lesson. So the kids ask lots of questions during the lesson, at least from what we saw. They're pretty engaging, and the lesson should be kind of informal, not super uptight or anything, engaging with the students. It's a definite benefit. So some of the current activities are some trebuchet designs, some zip line, water filtration, and electrical circuit designs. There's more to it than that, but we didn't want to bombard you with the whole list. When we did have our designs, we ran them by Rachel Hunter, who's one of the co-founders of the program, and Elizabeth Taylor is the director of STEM education outreach and K-12 programs here at MSOE, just to make sure we don't have any duplicates. So most of our learning research was geared towards the lesson design rather than the activity design, but we did incorporate some of these concepts into our criteria. So the first one was learning styles. That's just where we started because that's the first thing we thought of. Learning style is just the type of information you'd like to learn from. There's 3 types: visual, audible, and kinetic. Those are the 3 at least we focused on, and we found pretty quickly that there's no model that can predict what kind of learning style someone has, because it's purely preference based. So going along with that is that tailoring a lesson to someone's learning style doesn't actually help them learn it any better, contrary to common belief. Instead, having all 3 of them in a lesson or tailoring the learning
method or the learning style to the actual content is more important than Tony's learning style to the person. Cognitive styles are a bit different. They're more about like the inner workings of a person. They are about how a person thinks, solves problems, and remembers information. They can be predicted using models, empirical models, and tailoring the lesson to someone's cognitive style does improve learning. So the difference between them is that learning style is more about how information is presented, and cognitive style is more about the inner workings of the mind. Next, we looked into cognitive loading, which is a total effort taken by the brain to learn something new. There's 3 different types. There's intrinsic, which has to do with bridging the gap between previously known information and the new information. There's extraneous, which has to do with discerning which information is important. And then the third one is germane, which is most associated with learning achievement. The higher the germane load is, the more of an achievement there is. So add them all together, you have your total cognitive load, and try to keep it kind of low because everybody's kind of got a threshold. So misconceptions are bound to appear when we're talking about physics. Some of them can be very simple, just singular facts that are incorrect. Some of them can be entire foundational knowledge of science that could be wrong. It just depends. And one method we found that can help eliminate them is reputational tests, or I guess lessons in this scenario, which is just addressing one of the miscommunications and then immediately following it with some evidence to contract it. Augmented activation, something we found that has lots of different definitions in psychology, but in this context, it's a pre-reading or pre-lesson instruction that helps people know which information to look for while they're learning. So you can say, look out for examples of X, or look out for examples of Y, or try to find some things that conflict with what you once believed, and that will help the students determine what they should be looking for. So that using this strategy has shown to increase learning achievement. Finally, we have metacognitive scaffolding, which is an approach where students are encouraged to plan their approach to learn something before they do it. Then while they're going through an activity, they take a few moments to reflect at periodic intervals on where their trajectory is headed and if they're going in the right direction. At the very end, they do another reflection to see how the whole thing went, and then they reflect on what was good, what was bad, et cetera. That has been shown to increase learning achievement in students. There's some psychological concepts we wanted to try and integrate were emotions and affect. I never heard of affect before this, but emotion is more of a complex feeling that someone has, where affect is just kind of a general broad sense of are you feeling good or feeling bad. So we found some studies that showed that those with high levels of affect, positive affect, had increased levels of mental creativity, adaptability, and flexibility, which are all things that we want to promote in this environment, because the odds of them actually remembering most of the theory we talk about in the preliminary lesson is pretty low. But if they can remember their relationship and experience and take those other more broad skills with them after the lesson, that's going to be very important. Also, those with high levels of affect are more likely to pursue goals. So if we create a positive environment for the students to be in, then they're going to be more likely to pursue STEM again in the future.
All right, next we will discuss the constraints and criteria that help narrow down our designs along with develop them more fully. So starting with the constraints, you can see them outlined here. Our objective was to create 2 activities for the students, one taking place in an MSOB lab to expose them to that kind of environment, and then one that will be transportable or mobile in another sense, as there's over 20 locations nationally, so that they could take this to a different semester location. Next, each session we have 75 minutes with the students, and we're planning for up to 25 students. So that plays more into our budget because we want to maximize the interaction each student can have with the activity. Next, and most importantly, safety is a top priority for us. We're going to introduce any necessary lab protocol to the students, along with design experiments with safety built into them. Continuing, our experiments should be cost effective. We have a budget of $1,000, which is kind of flexible, but ideally we'd like to stay under that. And then finally, both experiments should be useful by the beginning of April, as that's when the session with the students will actually take place. And next, you can see our criteria outlined, comparing importance relatively among them. First of all, student freedom has the most importance as our experiments are focused on students. This is supported by the metacognitive scaffolding that we discussed earlier. And we want to make sure that students can take ownership and experiment with the different activities so that they can learn through doing. Next, we have learning styles. There's over 30 out there, but we focused on auditory, visual, and kinesthetic, which we hope to include all pretty equally so that every student feels engaged. And we thought that was really important. Next, transportability, that's the mobile aspect, which was also fairly important as STEM requested that, and we thought it was something nice that we could do. Continuing experiment cost was moderately important. This is the cost that STEM will have to pay out of budget to run the experiment every time. So we have to account for any components that might be broken on accident or on purpose. So we would like to minimize that. Just continuing segments, this is how each session will kind of be structured. We want to include theory, video, building, measure, and analysis segments. The theory will kind of introduce any equations and calculations that are prerequisite for the activity. And the video will kind of supplement that too. And then the building segment will take the longest amount of time. It'll be very hands-on, try and keep the students engaged. And then the measure and analysis segments will kind of summarize what they did, compare the calculations and the actual experimental values. And we thought it was important to have around 5 segments just so they're not doing the same thing for a long amount of time, just to keep them engaged. Next up, we have setup time. This is the time that either us and or the STEM staff will have to take to set up the experiment. So this is moderately important, but it doesn't directly impact the students. So it's more of a convenience for us. And then finally, the building costs. That's kind of the same constraint mentioned before. We can always file for a grant for more money, so it's not super complicated, which is why we rated it so low. And then here are just 6 of our designs that we chose to develop a little further before comparing. As you can see, the first 2 bolded ones are our final choices. And the next slides will kind of go through an overview, a design, what the lesson plan might look like, and an estimated cost.
So one of the activities that was chosen was a bending lab activity. This activity is designed to introduce students to stress and material strength. This has parallels to the activity that STEM already included the kids in, which is rowing. So because during rowing, a row would experience bending. So some engineering principles covered in this activity would be forces and free body diagrams, normal and shear stresses, bending, torsion, and actual stress modes, as well as some yield stress, flexural strength, modulus elasticity, some flexural modulus, as well as the aerial moments of inertia. Some key design features for this activity is a sliding mechanism that allows the moment arm to vary, a wood specimen, and this was chosen due to its low cost and ease of replacement, but also its relatively weak properties, and as well as it being compatible with the mechanics lab force fixture and the MSOE mechanics lab. Here's a simple free body diagram of the wood specimen. This force would be applied by the load ramp that these students will be able to manipulate to achieve this force. And that length X will vary across, you can go to the next slide. That length X would be varied by this slider, which will be able to slide back and forth. So some work that was done on this activity at the moment has been this spacer length, and this is quite important to determine because we want to prevent interference between the dowel and this center bolt. So to determine this spacer length, we developed this equation, which takes into account all of those heights. And using those equations of bending, deflection, as well as the angle slope equation, we were able to calculate the deflection and the XL, and these other ones were sort of based off of the CAD model. Some student objectives for the bending lab would be to, the students would be able to choose a force and length value from an array such as this. They will then conduct a pre-experiment analysis using the equations taught in the theory segment to see if the beam will yield or not. They will then conduct the experiment and do a post-experiment analysis to validate their initial expectations or correct any mistakes. The initial cost estimate for the first iteration for 2 test benches was $585. Our second iteration brought it down to $379.
Next up, we have the music activity. The current group of students at STEM is very musically inclined, and we thought it'd be cool to kind of combine physics and sound for the students. A lesson might introduce the theory of waves, different aspects of sound, frequency, and wavelength, and we're going to focus on stringed instruments in particular. And then here you can see our concept. So the objective for the students is going to be to produce a certain note. So we'll kind of help them figure out what frequency that corresponds to. And they'll be able to do this by adjusting the weight hanging over the pulley. This will increase or decrease the tension in the string. And they will also be able to change the length of the string. In addition to that, there will be a few different options for strings that they can compare, like a guitar string paracord, yarn, or silk spline and stuff like that. Some other things we're still looking into too are using water as the weight, which would just be kind of fun for the students and more cost effective. And we also hope to add 2 bridges right there to support the string a little bit better. And this experiment is pretty straightforward. The students obviously have some experience with sound, so there's a lot of parallels there. We estimated one experiment to cost about $70, so we hope to make at least 5 to increase every student's interaction with the experiment.
So the next 4 activities were activities that were not developed further due to being eliminated during our decision process. One of them being the boat drag activity, which was designed to showcase drag forces. Engineering principles that would have been covered would have been forces, free body diagrams, buoyancy, and spring mechanics, as well as some statics. Some key design features for this design would have been a tank of water with a submersible pump to simulate current flow. The boat would have been attached to the tank via a spring, which will allow the students to directly measure the drag force. 2 dampers would have been installed next to the boat to prevent any rotation, as well as a graduated cylinder to collect displaced water by the boat, and that would have been useful for calculating the buoyancy of the boat. Students would have been able to design their own boat using Legos or some type of 3D printed structure to kind of allow for variation in that drag force.
Next up, we have the Arduino kit activity. The idea behind this was to introduce the students to mechatronics, as that's likely a new concept for them. So the lesson might include going over some electrical concepts and different components typically found on a breadboard. Here you can see one idea for an activity that incorporates a screen and some push buttons. We thought it would be fun to introduce some competition and have them like compare their reflexes or something like that. And here's just a basic wiring diagram, actually from a lab here at MSOE, which is pretty cool. This illustrates some LEDs, resistors, and a push button. And we would give this to the students and have them replicate it along with a partially or completely made code that they can run. Another idea that's more complex would be to make an electronic piano, just like 1 octave, which we thought would be pretty cool, but very involved. And because there's only a few components and we're going to be buying in bulk, the experiment was relatively cheap at $30 for one.
Okay, so the next activity is the train yard activity. This one focuses on manufacturing and process engineering. So the students will be asked to create something out of molded Play-Doh parts. So each student will be at a different station in this track here. The material station is responsible for depositing and setting material to the mold stations, and the mold stations are responsible for making the pieces that the building station needs to complete the final object. So this train car kind of runs between them, and they're only allowed to transport things using that train car. So the lesson may include production lines, some queuing models, and manufacturing methods. So this is an example of what this molding station might look like. You'd have this mold chassis and then a swappable mold that you could switch out depending on which piece the builder needs. And then it would just be like in this panini press looking thing where you put the Play-Doh in there, punch it down, and you have your shape, and you can set it on. So then your material station will have this piston filled with Play-Doh, and then you could pull down this lever, pushing the piston and extruding the material at the bottom. The material station will also have this gauge here so they can measure how much material they've extruded, and it would reset every time they put the lever back up. And these tick marks, there will only be a couple of them, but correspond to which mold pieces would be needed. So we could do the calculation to make sure they're all even interval with one another. One more back. The cost for the experiment was not determined because it was eliminated very quickly. This design has very low design freedom, and they also have an activity already comes that center stern. So the next one is the gear train activity.
students will be asked to build a gear train out of a bunch of different gears to accomplish a task, whether it be torque related or speed related. So they'd be given this base plate here where they can put shafts in these holes and then put gears and stack them on top of each other. And then they just link these gears together to accomplish some sort of task. So the lesson planners include gears, gear ratios, and then some real life examples. So here's an example of one of the activities was just to spin a propeller as fast as possible. And then there's a spring here that would lift off, and depending on the length of spring, that's how much lift force you have. So the students will be able to easily measure that. Because gears, we want to choose multiple different sizes of them. Most gears aren't spec'd like out based on diameter. They're defined based on the gear tooth number. So that's more circumference based. So having these evenly spaced holes isn't going to allow the gears to mesh up perfectly every time. So instead we use this rail system, where instead of having multiple dots, we just have one slot that can move along a rail. So then you can put the gear through the top and then slide them together so that they mesh every time. The cost for this experiment was pretty high. We wanted to have 5 of them, and it was about $110 each. This cost is so high because of the plastic gears, metal gears. They're both pretty expensive if you want to get large ones that are easy to work with. So
The way that the process that we used to decide on which of those designs we would develop further was by developing our criteria table, which lists out all 7 of our criteria along with their associated weight, as well as this table enabled us to score each activity on a 1 to 10 scale. So we split up the process into 2 rounds. The first round was designed to eliminate 2 activities that we believe didn't have potential to become final contenders. The second round was a lot more in detail across all 7 criteria. So for our first round, we only considered our 2 most important criteria, being learning styles and student design freedom. Based on these 2 criteria, the Arduino and train yard activity were eliminated due to having a very low student design freedom. And for our second round, it was a lot more in detail across all 7 criteria. So our boat and bending activities were split up into a lab version as well as a transportable version. With the lab activities, the bending activity ended up having the highest criteria score at 9.1. And for our transportable activity, the music activity won at 9.8.
So for our steps going forward on the design path, we want to finish our designs within the first 3 weeks of coming back from break. So we want to order some parts, do a prototype run, make sure it works, test it, revise the design, and order the rest of the parts and assemble it. On the bottom side, we want to do some lesson planning in the first 3 weeks in tandem with designing the finished product. We want to practice the lesson and then revise it and repeat that as many times as we need to make it perfect. Finally, we want to do a full session rehearsal, the entire thing, including the test apparatus, and that should be due by the 1st. So we have a bit of room to work with at the end there, about a week and a half, it'll probably get eaten up by waiting for parts. So
Our team just wants to extend our gratitude to all those listed here and those who are not. We really appreciate all your input and support for our projects.
Okay, thank you. Okay, got a couple minutes for questions. Start with committee first. Sure, you're chomping at the bit.
You guys were only a few slides away from having one of the best formatted slide decks that I've seen in years. The tables were too much. You talk about cognitive load, those tables they like show all the groups put them up, and it's just like your mind goes numb. So like fix those slides and your deck looked like great. There were a few other slides that maybe had a few different words, but it was good. I think it's actually hard.
Yeah, I got a couple. So the bending lab. So first off, you had like these 6 that you were considering, yes? And you are for sure going with the bending and the music?
Yeah, as of right now, those are the ones that we have decided.
Okay. So I thought it was a little unusual that you spent, 5 or so minutes talking about the ideas that you're not going to use, but okay. So you're going to do this experiment in S214. Is that the idea? You're going to hook it up to like those frames? All right, and so you want to try to get them to come away with like what concepts? I think you mentioned yield.
Yeah, some yield strength or flexural strength.
Right. So wood is, I don't know if it's the best choice for like demonstrating yield, right? So wood
Yeah.
can be brittle in some ways, so I just caution you about the material choice for that experiment if you're trying to like teach yield as a concept. Right, okay. So that's that one. And then for the music one, I would have liked to see a little bit more about the theory itself and kind of talking about what's the material for the string that you're going to use, what lengths are required to get certain notes and certain changes, how much tension do you need to change from one note to the other. I think that would have been kind of nice to see. So do you know about how much weight you're talking about here? Because if it's going to be a mobile thing, you should be aware of like how much load it's going to take to change the notes and things like that. So do you have any idea on that?
Yeah. Some way like the strings can support anyways, it's gonna be like 5 pounds. We're gonna need like a little more for the guitar one, so it has enough tension.
Okay, so you have a couple of different strings that you're gonna use?
Yeah.
Okay. Cool, that's good. All right, that's enough for me. Any other questions?
If you guys could speak a little bit more about exactly what data the students will be collecting in both experiments, and then maybe what you guys are gonna have them do with that data, or like what you're gonna plan to show them, similar to talking about this question.
Sure. So for the bending one, they would start with selecting the force and length values, and then using those, they would calculate the stress and see if that stress is larger than the flexural strength to see if it would fill or not. Then they would conduct the experiment, and it wouldn't necessarily be data collected, it would be more observation. So whether or not they're being yielded or not. If their initial pre-analysis determined that it should break, and during the experiment it did break, then that's great. But if they determined that it should break, but it did not, then clearly there was a mistake there somewhere, and the post experiment analysis should hopefully correct that.
Okay, it's more like a validation.
Yeah.
Okay.
And for the music one, we would like ask them to produce a certain note, and we tell them like what frequency that corresponds to, and we'll give them like the linear density of each string, and we have equations for that. And then similar idea, they get to change the length and width, and also calculate what the given length and width, what length and width they need for that frequency.
And I believe we would be using a mobile phone app to kind of record the notes.
Yeah, or some sort of tuner.
Yep.
Cool, thank you.
Have you guys considered like you have 75 minutes for each of these, right? Have you considered laying out a timeline for the 75 minutes about like, okay, these 5 minutes, we're gonna talk about this theory and then have them go do this thing and then 10 minutes on this and then 10 minutes on that? Have you like,
So
Wait,
we're gonna do some lesson planning next semester.
Yeah.
That's one of our things that we'll definitely be.
Yeah,
Also-
because you want to plan it for yourself when you do it, but this is also an activity that you're gonna leave with staff to start personnel or potentially send it to somebody at a different location.
Yes.
And they want to have a clearly defined plan for those. They can change it, of course, when they get it, but you want to have a detailed plan.
Yes, sure.
That will also include like the 5 segments we introduced too, so we can kind of vary how much equation, lesson, video time and stuff we need to.
that probably ends up being more important for the music one, because that's like the mobile one, quote unquote, that you guys have. Okay. Any other questions? I guess we can open it up to other people in the back. Yeah, go ahead. Yeah, please.
I think just basic math skills, like maybe a little bit of algebra would be good. We don't expect them to know much physics at all because we know it's not really taught in school, at least not a high degree. So kind of going back to cognitive loading, there's the intrinsic cognitive load, that's the gap between what they previously knew and what they now know. We can't really control that. So we're just gonna try to dial it back as much as we can and start from the ground up with our teaching the lessons that they're lessons.
If you'd like us to go through that, feel free to reach out to our staff at the STEM Center, because I know a lot of the schools we serve here, the math is, we have some students who like addition and multiplication could be a stretch, and others might be ready for algebra. So if you'd like help differentiating, let us know. I think you have some really complex topics, and I don't want them to get stuck on the math and use that for your remaining power.
Yeah.
I think as an alternative and how to having an equation with 3 different parameters in it or 4 different parameters. You can just have them sort of clear. Is the strength of this going to be increasing or decreasing with the length? Not making an equation, but what is the relationship? Yes. Is it gonna get longer? If longer is gonna make it weaker, or longer gonna make it stronger? That's the thing.
Another approach you could do with that is how to start with that, try to find those relationships and then show it at the end of the equation. That would.
Yeah, exactly.
Good questions.
Okay, we're at 11:59, so right on time. So thanks, guys. All right, so that's the end of this session. We'll start up again at 1 o'clock. Yeah.
Thank you.